Okay, so here's our second video in the prime series. Oops, 148b. Why are there infinitely many primes? Okay, so this is a proof, I think it's due to Euclid. And it relies on something called the fundamental theorem of arithmetic that says you can factor numbers into primes. Like 24 is 2 times 2 times 2 times 3.
Yeah.
So the fundamental theorem of arithmetic says any integer can be factored in primes in a unique way.
Yeah.
Up to order. Like I could also say this was 2 times 2 times 3 times 2. But any factorization of 24 is going to have 3 2's and 1 3.
Yeah.
Okay, and by the way, this is why we don't say 1 is prime.
Yeah.
Because if 1 was prime, then this theorem wouldn't be true, because it could be 2 times 2 times 2 times 3 times 1.
Yeah.
Or 2 times 2 times 2 times 3 times
1 times 1.
1 times 1.
And then there would be infinitely many
Right.
things.
So we want the fundamental theorem of arithmetic to be true.
Yeah.
Okay. Now, say we had a finite number of primes. This is going to be a proof. Say we had only finitely many primes. Okay, so it'd be 2, 3, 5, 7, ... all the way up to some maximum prime that we'll just call capital P because it's the biggest prime. Okay? Now, let's multiply all these primes together. So we make a new number, m, which is 2 times 3 times 5 times 7 times ... times p.
Yeah.
Okay? Now, let's take a look at m plus 1. By the fundamental theorem of arithmetic, what can we say about m plus 1?
M plus 1, you can't factor it.
Well, hold on.
Well, you could.
What does the fundamental theorem of arithmetic say about any number?
You can factor it into primes.
You can factor it into primes. So m plus 1 can be factored into primes.
Yeah.
Okay, somehow. Is m plus 1 divisible by 2? Can you answer this question for me?
No.
Why not?
Because it's 1 more than a multiple of 2.
Is m plus 1 divisible by 3?
Actually, no, because it's one more than every multiple.
Okay, and it's not 5, not p. So m plus 1, let's say this is some prime 1 times some prime 2. We don't know what it is. Some prime n.
Yeah.
It can be factored into primes by the fundamental theorem of arithmetic. But none of these primes that it factors into are any of those primes. And what did we assume about these primes?
Those are the only primes.
Those are the only primes.
Turns out there's more.
Turns out there's more.
So it's contradiction.
It's a contradiction, and our assumption was there were finitely many, that we could list all of them. Okay? And that turns out a contradiction, so therefore what?
Therefore there are infinitely many.
Infinitely many primes. High five. All right. Ready for the next one?
Yeah.